Hello everyone, I am Gabriele Ara. Today, I'm here to show you the framework that we developed at Scuola Superiore Sant'Anna of Pisa, in collaboration with Ericsson, to perform a comparative evaluation of kernel bypass mechanisms for high-performance inter-container communications. What I'm going to show you today are the results of a joint work of me, Professors Tommaso Cucinotta and Luca Abeni from Scuola Superiore Sant'Anna of Pisa, and Carlo Vitucci from Ericsson. The context of this work is represented by network function virtualization. Nowadays, infrastructures of Internet service providers are composed of a set of custom hardware appliances, from simple routers to complex intrusion detection systems. Traditionally, these kind of infrastructures are sized for the peak hour, which means that most of the time, some of the allocated resources are underutilized. In the context of network function virtualization, ESPs can improve the flexibility and scalability of their infrastructures by moving from custom hardware devices to equivalent software implementations of the same services. These new implementations, called virtualized network functions, can then be deployed on a modern cloud infrastructure to leverage their flexibility and the capability to scale on demand. These virtualized network functions, once deployed on the cloud, must be properly isolated from each other. This can be done using traditional virtual machines, but the cost of this approach in terms of performance is too much for the high demands in terms of throughput and latency of virtual network functions, in particular with respect to their hardware-based counterparts. For this reason, OS containers can be used instead of virtual machines to isolate these applications. Containers are much more lightweight and achieve isolation merely by means of control groups and namespaces. Thus, the cost in terms of performance is minimum and comparable to running these applications on a host operating system. Applications deployed on containers typically communicate using network system calls. However, the overhead of system calls like send and receive are too big for the amount of traffic that these applications exchange. Grouping multiple packets in bursts, reducing the number of system calls to be executed to one per burst of packets, certainly helps. Still, it is not even nearly enough to achieve the desired performance. This because switching from user to kernel space and vice versa is very expensive. We need some solution to avoid switching at all, both when communicating locally with other applications deployed on the same host and when exchanging data from one host to another. For local communications, we can use VirtIO devices with user space drivers to exchange data among applications deployed inside containers on the same host, without involving the kernel at all and always remaining in user space. For host-to-host communications, we can use the Data Plane Development Kit framework, or DPDK, which implements network drivers in user space. This framework, initially developed by Intel for its network cards, has been expanded a lot over the past years, and now it supports VirtIO devices too. Hence, we can use DPDK for both local and remote communications, using its unified interface without worrying about which underlying medium will be used. For local communications, it will use VirtIO virtual devices, while remotely it will directly access the physical network device. This solves the problem of point-to-point communication between two applications. However, to fully utilize the resources of a machine, we should deploy multiple virtualized network functions on the same host. The switching of packets from and to multiple applications can be done in software too, employing one among the networking solutions presented on this slide. Briefly, we have the DPDK Basic Forwarding application, which is a simple application that can connect pairs of virtual network ports but does not implement any actual switching functionality. Then we have OpenVSwitch and Vector Packet Processing, or VPP, which are both DPDK-based implementation of fully fledged virtual switches. And finally, we have SnapSwitch, which is a more configurable virtual switching application. More details on each of these solutions will be provided later during this talk. There is another alternative solution than using VirtIO-based devices to exchange data locally. The alternative approach consists of using a physical network card that supports single root I/O virtualization, or SR-IOV, to interconnect containers on the same machine. A network card that supports SR-IOV can expose more than one virtual device called virtual function, which can be addressed independently by each container. Each virtual function contains separate buffers and hardware that can be used to move data from and to applications. In this case, each application deployed in a container is reserved a virtual function, which it can access without any interference from other containers. Local switching among containers deployed on the same host is then implemented directly in hardware inside the network card, which will move packets from one virtual function to another, while the outgoing traffic is forwarded to the network cable. This represents an alternative to virtual switches implemented in software that use VirtIO ports, since we can also use DPDK user space drivers and bypass the kernel when accessing each virtual function of an SR-IOV device. At this point, we have seen that there are multiple solutions to realize an infrastructure based on network function virtualization. Choosing one based only on qualitative features is not a very good idea. We need quantitative evaluations of each of these solutions. To tackle this problem, we developed a framework that can be used to evaluate the performance of each alternative illustrated so far when used in real use case scenarios. The main characteristics of this framework are the automation of the setup of each individual network technology to be compared on the desired machine, and the automated deployment of some custom applications inside OS containers to measure system performance. Performance is evaluated under three different aspects, namely throughput, round-trip latency, and scalability of these applications. Let's see more details about this framework. The framework consists of a set of software tools that automate most of the processes of running performance evaluations on the target machine. These tools automatically install the dependencies of the framework on an Ubuntu-based Linux distribution, including the software virtual switches that we have seen before. Finally, we have a set of benchmarking applications that we developed to test networking performance. These applications are to be used in pairs, depending on the kind of test that is carried out. The sender and the receiver applications are used for throughput and scalability tests, while the server and client application are used for round-trip latency tests. Each of these applications generates or consumes bus of packets exchanged over the local network. They are all built on top of an API abstraction layer that masks the difference between the standard POSIX API and the DPDK one. This way, each application can use the same logic to exchange data both via kernel or through one among the kernel bypass solutions that we have seen before. In the latter case, DPDK is used to access either VirtIO or SR-IOV virtual functions directly from user space. When performing an experiment, these applications are automatically deployed inside containers according to some specified configuration. The three possible scenarios are the following. The first one is to test the performance of UDP and row sockets and the in-kernel software switch, which is called Linux Bridge. The second one is to use a software implementation of a virtual switch, using VirtIO user space devices as a communication medium. And finally, the last one is to use DPDK in combination with an SR-IOV device, which uses a hardware switch to forward packets. Now that we've seen the features of the framework, let's move on to how we used it to evaluate system performance in a variety of application scenarios. To do so, we deployed multiple applications either on one or multiple hosts, evaluating in the different configurations the achieved throughput and round-trip latency, and how the throughput is affected by the number of applications deployed on each host, that is, the scalability of the system. First of all, let's talk about the performance of the in-kernel software switch. Using simple UDP or row sockets on our reference server machine, it is not possible to reach even 500,000 packets per second as maximum throughput. As mentioned before, the performance of the kernel-based solutions are not suitable to run typical NFV applications. That's why from now on, we will show only solutions achieved with mechanisms that bypass the Linux kernel. Let's consider the maximum throughput achieved by each kernel bypass solution when a single pair of sender and receiver applications is deployed on a single host, hence performing only local communications. In this plot, we are showing the maximum throughput achieved by each virtual switch in millions of packets per second with respect to the size of the packets exchanged by the two applications. From our experimentation, we noticed that for a fixed packet size, the receiving rate of the receiver application is always able to match the sending rate of the sending application up to a certain maximum value is reached. That is why here we are showing the maximum receiving rate that we registered for each packet size. Of course, since we are considering throughput, in this plot, the higher the better. Let's see how each software virtual switch performed in this configuration one by one. First, we have snap switch. This switch provides a great flexibility to system deployers, since its packet processing flow is fully customizable, but it has the lowest performance among the solutions that bypass the Linux kernel. Then we have OpenVSwitch, which is an open-source fully-fledged virtual switch. As we can see, for smaller packet sizes, its throughput in terms of millions of packets per second is higher than snap switch. But as we increase the size of each packet up to the maximum transmission unit of 1500 bytes, its performance are very similar to snap switch ones. Then follow FD-IO vector packet processing, or VPP, and DPDK's basic forwarding application. The first is another fully-fledged software virtual switch developed by the Linux Foundation that implements Cisco's vector packet processing technology, hence its name. This means that VPP can process packets in batches and benefit from the exploitation of both data and instruction cache locality to achieve improved performance with respect to OpenVSwitch. It is remarkable that its performance are so similar to DPDK's basic forwarding application, since the latter does not implement any switching functionality at all. It just forwards any incoming traffic from each port to another statistically assigned port. Hence, it cannot be used in a real use case scenario where VPP can be deployed anywhere. Since VPP can attain similar performance, we can conclude that its batch packet processing features can effectively distribute its packet processing overhead among incoming packets. Lastly, we have the alternative solution of offloading all network traffic to an SR-IOV compatible network card. As we can see from the plot, this is a solution that is able to achieve the highest throughput performance on a reference machine, thanks to the exploitation of its embedded hardware switch. Notice that while the throughput in terms of millions of packets per second clearly decreases as we increase the size of each packet, if you consider the throughput in terms of gigabit per second instead, it is actually increasing, as shown in this new plot. The maximum throughput in terms of gigabit per second is always achieved when the packet size reaches 1500 bytes. These plots all consider only one pair of sender and receiver applications deployed on the same host. If we deploy more than one pair on the same host, we obtain other interesting results. In this case, we compare the maximum throughput achieved by each sender and receiver pair with two different packet sizes when varying the number of pairs deployed on the same host. In this slide, on the left, we have the maximum throughput achieved when exchanging packets of 64 bytes, while on the right, we consider 1500 bytes per packet. As we can see, in all the scenarios, each pair is affected by the interference of the other ones, achieving smaller and smaller throughput as we increase the number of pairs from 1 to 4. This can be easily explained if instead of considering the throughput achieved by each pair separately, we consider the total volume of network traffic that flows through each virtual switch. As we can see from the new plot on the left, the total amount of throughput flowing through each virtual switch remains unchanged when the size of each packet is relatively small, about 64 bytes, independently of the adopted solution. This means that the available resources are distributed equally among the application pairs. However, if we consider bigger packet sizes, like 1500 bytes, on the right, we notice that there is one solution that can actually scale pretty well. keeping up with the increased volume of traffic generated. And that solution is to use the hardware switch embedded inside the SR-IOV-enabled network device. From these plots, we concluded that while for SR-IOV the major limitation is represented by the number of packets that are exchanged through the network, for VirtIO-based switches, the major bottleneck is represented by the capability of the CPU to move data from one application to another, which depends on the total number of bytes that are actually exchanged. Now, let's move on to what happens when we deploy two applications on different directly connected hosts. In this case, we can consider the performance of only a small subset of solutions because of the limitations of the others. In this plot, we can see that each solution, OVS, VPP, and the SR-IOV device are able to match the physical limit of the Ethernet cable used to interconnect the two hosts when we increase the packet size accordingly. In addition, on the contrary of before, software virtual switches seem to have the advantage here once we reach bigger packet sizes. Most probably because they use less of the resources of the network card with respect to offloading entirely the packet processing operations to hardware. Anyway, in general, for bigger packet sizes, the limitation of the Ethernet cable is the most dominating factor. This is true also if you try to deploy multiple sender and receiver pairs among two directly connected hosts. Again, using bigger packet sizes, the scalability of each solution is mostly capped by the capability of the network cable. Now that we have seen the results of our throughput and scalability performance tests, let's move on to round-trip latency performance and see how each solution performed locally on a single host. In this plot, we compare the average latency achieved when exchanging a small number of packets per second between a client and a server application deployed on the same machine. Of course, since now we are considering the latency dimension, the lower the better. In this case, SnapSwitch obtains very poor performance with respect to the other solutions. This explains also partially its poor performance in terms of throughput. To better visualize the differences among the other solutions, from now on we will not show SnapSwitch in our plots. If we remove it, we notice that most software-based solutions perform similarly from this point of view, while SR-IOV performance depends on the burst size. If we group packets sending 4 packets per burst, as shown on the left, the latency introduced when using SR-IOV is bigger than the others. However, if we increase the bus size from 4 to 32 packets per bus and beyond, as shown on the right, SR-IOV achieved a smaller average latency. This is true when the client and the server applications are deployed on the same machine. If we move on by deploying the client and the server on two distinct directly connected hosts, of course the average latency increases for all solutions. However, this time SR-IOV achieves always the smallest latency. This can be easily explained too. When using VirtIO-based software switches, 2 levels of forwarding are introduced with respect to the SR-IOV case. The 2 software instances, each running in their respective hosts, introduce additional computations to the ones already performed in hardware by the SR-IOV device anyway. These were the most representative results that we obtained from our experiments. If you are interested, our paper presents some more results in more details, of course. And this brings us to the final conclusions. As we have seen, the framework that we developed can be effectively used to perform a variety of performance evaluations of both single and multi-host scenarios. With it, we were able to compare the most representative solutions that can be used to realize an NFV infrastructure, showing that the solution that performs better in the various situations is to offload network traffic to the SR-IOV device when available. Of course, these results may change as the software switches presented in this work can receive performance updates and improvements. In the future, we plan to expand the framework by considering even more solutions available on the market. For example, including NetMap, which is another fast data plane networking framework available for both Linux and FreeBSD machines. If you have any questions, you can contact me at the address shown in this slide. I'll be very happy to reply. And of course, check out the framework on GitHub. Thanks for watching.